The title of the first module, Group Introduction. Today we are going to see about groups. Let us start from the introduction of a groups. The modern treatment of abstract algebra begins with the simple abstract definition of a group. This simple definition quickly leads to difficult questions involving the structure of such objects. The term group was coined by Galois about 170 years ago to describe sets of 1-1 functions on finite sets that could be grouped together to form a closed set. With that further ado, let us dive into the course. To define a group, we require a non-empty set together with the binary operation. Next, we are going to define the formal definition of group. As in the case with the most fundamental concepts in mathematics, the modern definition of group that follows in the result of a long process. The set is a collection of well defined objects, as we know, and the operation is a function that acts on two elements and results with a single element. For example, addition, multiplication, division, these are the operations defined on number system. Now, we need a non-empty set. We take this as G and we need a operation. The operation we denote it as star. For our convenience, we take it as star. This set together with this operation have to satisfy some property. Let us go through the property first. First one, closure. Closure means A star B is in G for all A B in G, which means that we have to take two elements A and B in a group. The resulting element, after applying the operation, the resulting element must be in G. If the operation satisfies this property, then the operation is called binary. The second property, associate, which is nothing but we can operate the first two element with the third, which is always same with the operating the last two element with the first one, which means A star B star C equal to A star B star C for all A B C in G. If a set together with this operation satisfies both the property closure and associative, then the set is called, the set with the operation is called semi group. Third one, identity. Identity means we have to find an element, we denote it as E. There exists an E in G such that A star E equal to E star A equal to A for all A in G. So, this element is called identity of the set, and if the group, if a set with the operation satisfies the first three property, namely closure, associative and identity, then the set is called monoid. And the fourth property, inverse. For every element A in G, we have to find an element, we denote it as A inverse of G such that A star A inverse, which is equal to A inverse star A, which is equal to E, which means for every element we have to find another one element in the set which has to satisfy this property. The E is nothing but the identity we have taken from the property 3. So, if the set together with this operation satisfies the first four property, I recall it again, closure, associate, identity and inverse, then the set together with the operation is called group. Next, there are one more property is there, namely commutative. Commutative is nothing but A star B equal to B star A for all A B in G. So, we can able to operate the element in the both the ways, A star B equal to B star A. If the set and the operation satisfies this condition, then the group with this condition, it is called abelian group. So, abelian group means it has to be satisfied the all the five properties. Once again I repeated, closure, associate, identity, inverse and commutative. Suppose a group which a set together with the operation satisfied the four condition, which is called group, and which is not satisfy the last property, namely commutative, then the group is called non-abelian. In 1890, Jordan introduced the term abelian group to honor Niels Henrik Abel, one of the foremost mathematician of the 19th century. Next, we define the formal definition of non-abelian group. A group is non-abelian if there is some pair of elements A and B in G for which A star B not equal to B star A. For clear understanding, we should look for some examples. Let us see some examples. We consider the set of all integers together with the operation plus. So, we define a group, we need a set with an operation for our convenient and the well known set, the set of all integers with the familiar operation plus. So, that means we have to check this form a group or not, for which we have to check the 4 properties. The first one, closure. Clearly, sum of any 2 integer is again an integer, therefore, a plus b belongs to Z for all a comma b in Z. Therefore, closure property is very clear. Next, we are move on to the associative. So, this is also almost clear that a plus b plus c is always equal to a plus b plus c. So, this is always true for the addition. Therefore, Z comma plus satisfy the associative property as well. Next, we are moving on to the identity. Identity means we have to find an element such that a plus that element which is equal to that element plus a equal to a. Can you able to guess what is the element? Yes, it is 0, a plus 0, 0 plus a is a for all element in the Z. Therefore, 0 is the playing the role of the identity. Therefore, the element 0 is the identity in Z plus. Next, we are moving to the last property called inverse. So, which means we have to find an element a plus some element which is equal to this element plus a equal to e. So, in the previous property we identified that the identity element is nothing but 0. Therefore, we have to find an element such that a plus that element is 0. So, obviously that element is nothing but a plus minus of a. So, now we have to check one more thing, that minus a is also be the element in the set Z. It is clear for whatever may be the integer, the minus of that integer is also be the element of the integers. So, this properties hold. Therefore, Z together with the operation plus satisfies the first 4 property. Therefore, the Z plus is group. Next, we on to the last property, namely commutative property. We have to check this because we have to find whether the group is abelian or not. So, it is also again clear that a plus b equal to b plus a for all a in a comma b in Z. Therefore, commutative property holds for Z comma plus. Therefore, Z comma plus is an abelian group. For the next example, we are taking the same set Z together with the operation minus. So, now again the closure property, we know that the suppression of any 2 integer again an integer. Therefore, a minus b belongs to Z for all a comma b in Z. So, therefore, the closure property is satisfied. Therefore, the operation minus is binary operation. Next, associative. In general, the operation minus does not satisfy the associative property in Z. For example, a minus b minus c not equal to a minus b minus c. For which we are consider an example for this, 2 minus 3 minus 4, you can check this, 2 minus 3 is minus 1, minus 1 of minus 4 is minus 5, whereas 2 minus 3 minus 4. So, now first we have to operate 3 minus 4, therefore, this is minus 1, 2 minus of minus 1 is 3. Therefore, clearly minus 5 not equal to 3. Therefore, in general this associative property does not hold for the operation minus in the set of all integer. Therefore, Z minus is not a group. Next, we move on to another example with the same set of integers together with the different operation, namely product. So, we consider the set of all non-zero integers Z set different with 0 and the usual multiplication cross. We have to verify that this form a group or not, which means we have to verify the 4 properties. The first one, closure. Clearly, the product of any non-zero integer is again a non-zero integer. Therefore, a cross b is an element of Z star for all a comma b belongs to Z star. Next, associative. Clearly, the product of a cross b cross c which is equal to a cross b cross c for any non-zero integers a comma b comma c belongs to Z star. Therefore, the non-zero integers together with the operation product satisfies the closure and associative. Next, the third property, identity. So, identity means we have to find an element for which a cross that element which is equal to the element cross a must be a. So, we have to find such an element. So, in product 1 reserve that element, therefore, a cross 1 which is equal to 1 cross a equal to 1 for all a in Z star. Therefore, 1 is an identity element. Therefore, identity law is also hold. The fourth one, inverse. So, we have to find an inverse for each element. So, A cross some element which is equal to that element cross A which is equal to E, we have seen that E is nothing but 1. Therefore, we have to find an element A cross some element which is equal to 1. So, in set of all integers A cross 1 by A equal to 1. Therefore, we have only A cross 1 by A equal to 1. In integers, take any integer, for example 5, but 1 by 5 it is not an integer. Therefore, in general 1 by A is not an element of Z star except for A equal to 1. Therefore, the inverse property does not hold even though there are some inverse exist, but the inverse is not in the set. Therefore, inverse property does not hold, but it satisfies the first 3 property. Therefore, Z star comma the usual product is a monoid. Next, we can check for the commutative. The commutative law is always hold for product. So, A cross B equal to B cross A for all A comma B in Z star. Therefore, commutative law always hold for Z star comma product. Next, there are one more operation remaining in set of all integers, that is division. Therefore, we again check the set of all non-zero integers together with the operation division is form a group or not. Let us check the first property closure. We know that A divided by B is not, in general it is not an element of Z star. For example, take 2 and 3, 2 and 3 both of them element of the integers, but 2 by 3 is not an element of the integers. Therefore, even the closure property does not satisfy. Therefore, the division operation is not even a binary. Therefore, the Z star comma integer set of all non-zero integers together with the operation division not form a group. So, now we are familiar with set of all integers. So, set of all integers together with the operation addition form a group, even it is an abelian group, but set of all integer together with the operation minus not form a group. Set of all non-zero integers together with the operation product and division not form a group. Now, we are consider another important set of all real numbers. So, now consider set of all non-zero real numbers together with the usual product cross. R star denotes set of all real numbers with set minus 0. This means set of all non-zero real numbers. We are just avoiding 0 from the real numbers. We have to check this R star comma cross form a group or not. Closure. Clearly, A cross B is an element of the set of all non-zero real numbers for all A comma B belongs to R star, because product of any two real number is again a real number. Therefore, this closure is always true. Next, associative. Associative is obviously clear. A cross B cross C equal to A cross B cross C for all A comma B comma C belongs to R star. Next, we move on to identity. That means we have to find an element A cross some element which is equal to that some element cross A equal to A for all A belongs to R star. So, here again in product the element 1 doing deserve this 1, therefore, A cross 1 cross A equal to A for all A belongs to R star. This 1 is also an element of the non-zero real numbers, therefore, 1 satisfies the identity property. Next, the last property for the group inverse. So, we have to find an element for every element A cross that element which is equal to that element cross A is an identity. As we seen in the third property, the identity is 1, therefore, we have to find an element A cross some element equal to 1. So, again in multiplication A cross 1 by A equal to 1, therefore, 1 by A may be the inverse of every element, but we have to find that this 1 by A is an element of the non-zero real numbers. Yes, of course, in case of non-zero real numbers, since we are avoiding 0, 1 by 0 is undefined, therefore, the 0 is eliminated from R star. So, this is the reason we have removed 0 from our set. Therefore, 1 by A belongs to R star for every non-zero real numbers. Therefore, inverse property also again hold for R star comma cross. Therefore, R star comma cross form a group. So, again we have to check one more property for verifying the abelian or not. So, commutative property A cross B equal to B cross A for all A comma B in R star. Therefore, commutative property is always hold. Therefore, this R star comma cross form an abelian group. Now, we are going to use another technique, namely Cayley table, for checking a group property for any finite set. Cayley table is an effective tool to find whether a finite set together with an operation is a group or not. A Cayley table describes the structure of a finite group by arranging all the elements in a square table. It is named after the 19th century British mathematician Arthur Cayley. In the first example, we are considering set of all cubic roots of unity g equal to 1 omega omega square under its multiplication. So, we take the set g equal to 1 omega omega square, which are nothing but the cubic root of unity. Therefore, omega power 3 equal to 1, the operation is the product here. Okay. So, now we are going to check whether this set together with the operation product form a group or not by using the Cayley table. So, as we already said, Cayley table is a square table by arranging the elements of the set by row and columns. Therefore, 1 omega omega square are the elements of the group. Therefore, we are arranging the rows and columns by row 1 omega omega square and by column 1 omega omega square. We are going to apply the operation product. So, how we do this? First, we are fill the entire elements of the Cayley table by 1 into 1 is 1. Therefore, we have placed 1 here, 1 into omega which is equal to omega, therefore, omega is placed here, 1 into omega square is omega square. In the next row, omega into 1 omega, omega into omega omega square, omega into omega square equal to 1 because omega cube is 1. The last row, omega square into 1 omega square into omega 1, omega square into omega square which is equal to omega power 4. Since omega power 3 is 1, this is equal to omega. This is how we are enter all the elements of the Cayley table. Now, we move on to the properties. The first properties says closure. Closure means the product of any two elements is again an element of the set. Here you look at all the entries 1 omega omega square, omega 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 square, omega square 1 omega. Therefore, all the entries of the tables are the elements of the group. Therefore, closure property is very clear from the table. Next, the associative property, it can be also clearly verified from these 9 entries. The associative is always true. The next property, identity. So, we have to find an element from this set which satisfies the property that A star the element which is equal to the element star A equal to A for all A. So, here you look at this 1 dot 1 is 1, 1 dot omega equal to omega, 1 dot omega square equal to omega square. Therefore, 1 doing the identity properties. Therefore, any element dot 1 is equal to the same element. Therefore, 1 is the identity here. The last property, inverse. So, we have to find an inverse for each of these elements. Here note that 1 into 1 is 1. Therefore, the inverse of 1 is self inverse 1. Next, we have to find the inverse for omega. So, that means omega is here. We have to find the entry 1 among these 3. So, the entry 1 is here. Therefore, the inverse of omega is omega square. Therefore, omega into omega square equal to 1. Similarly, the other way, omega square into omega is also 1. Therefore, the inverse of omega is omega square. For the last element omega square, come back again here, omega square, the entry 1 is here, the corresponding entry of the column is omega. Therefore, omega square into omega is 1, and the other ways omega into omega square is also 1. Therefore, the inverse of omega square is omega. Therefore, all the 3 elements has an inverse. Therefore, the inverse property is also satisfied. Hence, the cubic root of unity together with the operation product form a group. Again, you can check this is also satisfies the commutative property. Therefore, this form an abelian group. More general, we can consider one more example, the set of all nth root of unity. The elements are 1 omega omega square up to omega power n minus 1. The similar way, you can able to draw any Cayley table for a finite set. You can try to find the Cayley table for 1 omega omega square up to omega power n, which is nothing but the nth root of unity, which means omega power n equal to identity. This set together with the operation product is satisfies all the 5 properties, and for this is also form an abelian group. Next we consider one more example, but this time the set is set of all integer modulo 4 together with the operation addition modulo 4. I hope you are somehow familiar with this set. Even then, the set Z4 is nothing but the element 0, 1, 2, 3. So, the element of Zn is nothing but the element 0, 1, 2 up to n minus 1. Now, we come to the operation. We are considering here the addition modulo 4. The addition modulo 4 means we have to add the 2 elements with the addition modulo 4, means a plus addition modulo 4 b is nothing but a plus b if a plus b is less than 4, and otherwise it is r is nothing but the remainder when you divide a plus b by n. So, r, I repeat again, r is nothing. So, this is a finite set. So, we are going to find whether this set together with this operation form a group or not. So, since this is finite, we are again going with the Cayley table. So, the rows are entered by the element 0, 1, 2, 3, and the column is also entered by 0, 1, 2, 3, and the operation addition modulo 4. Let us see how we fill up this. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus addition modulo 2 is 2, 0 plus 3 is 3, because these are the elements less than 4. Therefore, we just replace addition modulo 4 by the addition. Next, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3. Again we have the elements less than 4. Therefore, in place of addition modulo 4 we just adding the 2 elements. Now, come to the last one. 1 plus 3 is actually 4, which is greater than or equal to 4. That means we have to find the remainder. So, the remainder, now we get 3 plus 1 is 4. When we divide 4 by 4, the remainder is 0. Therefore, 1 plus 3 is 0. Next column, 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 again 4. When we divide 4 by 4, the remainder is 0. 2 plus 3 is 5 actually. When we divide 5 by 4, the remainder is 1. The last column 3, 0 plus 3 is 3, 0 plus 1 is 4, therefore 0, 2 plus 3 5, therefore 1, again 3 plus 3 is 6. When we divide 6 by 4, the remainder is 2. This is how we fill up this entire Cayley table. Now, we are verifying the properties. The first property, closure. So, here again all the elements of the Cayley table, all the entries of the Cayley tables are the elements of C4. Therefore, the closure property is true. Again, associative is clear from the Cayley table. Now, we move on to the identity. So, that means we have to find an element which satisfies the property that A addition modulo 4 plus the element is A for all A. Now, look at here 0, 0 doing this job for us. That means 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3. Therefore, 0 plus any element is again that element. Therefore, 0 is an identity which is also an element of the Z4. Therefore, it satisfies the third property, identity. The last property, inverse, that means we have to find inverse for each element. Inverse of 0 is nothing but 0. Next, we have to find the inverse for 1. That means we have to find the inverse for 1, which means we have to find the identity from this column, the second column. So, the identity is 0, which is placed in the last row of this Cayley table, which means the inverse of 1 is 3. Therefore, 1 plus 3 is 0. Therefore, the inverse of 1 is 3. Next, we have to find the inverse for this next element 2. That means we have to find 0 here. 0 is in the third row of this Cayley table, which means the inverse of 2 is 2. Therefore, 2 plus 2 is 0. Therefore, the inverse of 2 is 2. Again, for the last element we have to find the inverse for 3, which means we have to find the 0. 0 is placed here. Therefore, the inverse of 3 is 1. 3 plus 1 is 0. Therefore, inverse of 3 is 1. So, we have find the inverse of 0 is 0, inverse of 1 is 3, inverse of 3 is 3. Therefore, inverse property is also satisfied, therefore, this form a group, and we have to check one more property for the abelian group. Here a plus b, a integer modulo 4 b is again b integer modulo 4, it can be easily verified. Therefore, Z4 together with the operation integer modulo 4 form an abelian group. So, it can be also generalized to the general set Zn. So, any integer n. So, Zn is nothing but 0, 1, 2 up to n minus 1 with the operation addition modulo n. So, the set Zn together with the property together with the operation integer modulo n form an abelian group.